Hello, welcome to Digital Electronics EEE 301, Lecture 8, Introduction to Number System. Number System and Course. Digital systems are built from circuits that process binary digits, but very few real-life problems are based on binary numbers. So a digital system designer must establish some correspondence between the binary digits processed by digital circuits and real-life numbers, events, and conditions. However, several other number systems are also important. For example, hexadecimal is used for represent memory address of the computer. It is also used in microprocessor, microcontroller, embedded system, where the system take input in terms of hex number and process it by converting into binary and then store it, display it in the hex number again. Use the laser pointer. The number system defines a set of values used to represent quantity. Name of your number system includes decimal, binary, octal, duodecimal, and hexadecimal. The base of a number system tells us how many distinct digits we have in a number system. So here you can see a couple of name of the number system and their base. So the binary number system base is 2, which you are already familiar with, I believe. Tertiary number system base is 3, quaternary number system base is 4, pental number system base is 5, hexamal number system base is 6, octal number system base is 8, decimal number system base is 10, duodecimal number system base is 12, and hexadecimal number system base is 16. So in this lecture, we'll discuss about the highlighted number system like binary, octal, decimal, and hexadecimal. How to convert from one to another, you'll get some idea in the later section of this lecture. So significant digits. You have a binary number, something like that. So your right side one, digit 1 is least significant, left one is most significant. So here 1 is least and this left side one is most significant. It is similar for other number system like for hexadecimal. Right side A is least significant, 1 left side is most significant. Counting in number system. With n digits or bits, we can count through base to the power n defined number starting with and including 0. The largest number will always be base to the power n minus 1. So what actually it means, you can get an idea with the example. Like for an example, the range of 2-bit number can be presented in binary number system is 0 to 2 to the power n minus 1. If you look at here, so here your base is 2, you are talking about binary number system, and also your n means how many bit, you have 2-bit number, so that's why the power is 2, so to the 2 minus 1 3, so 0 to 3, right? So total number is 2 to the power 2 4 2 to the power n. So this is what actually it says here. Like, so for any bit of number, so it can be represented like 2 to the power n minus 1, like base to the power n minus 1, right? So for 2-bit number it is 0 to 3 and total number is 4. For 2-digit number can be presented in decimal number system is 0 to, so here for decimal number system your base is, if you compare with this equation, is base is 10, and for 2 digit the power is 2, So the decimal number system can be represented between 0 to 99 and total number is 100. Okay, so it's the same for two-digit number in octal as well. So for octal base is 8, for two-digit base is 2, so there will be 0 to 63, so in total 64. For two-digit hexadecimal it will be 0 to base is 16, and for 2-bit 2 minus 1 and 0 to 255, so total will be 256. Counting in number system. So in binary number system, so you can represent 0 0 0 1 1 0 1 1, something like that. So you have 0 to 3. In decimal you have 0 to 99. For 2-bit it will be 0 1 2 3 4 up to 99, something like that. In octal you have 0 to 63, 0 1 2 3 4 5 6 7, then 10. So 0 to 7 is 8-bit, so let's say it's octal. There is no 8 and 9, right? It's going to 10 and goes on. For hexadecimal it is 0 to 9, then for 10 is A, for 11 is B, and it goes on up to F15, right? And it keep going on something like that. So there will be total 0 to 255. Example, counting in octal. We already discussed about that, but we'll get the idea how it works for if a number system. The largest octal digit is 7, right? So that is counting in octal. A digit position is incremented upward from 0 to 7. Once it reaches 7, it recycles to 0 on the next count and causes the next higher digit position to be incremented. So the highest number in octal is 7. If it reaches 7, then it goes to 0 again, and it goes again 0 1 2 3 4 5 6 7, again 0, something like that, right? With an octal digit position we can count to 8 to the power n minus 1 for a total of 8 to the power n different values. So for 3-bit octal, so it will be 8 to the 0 to 8 to the power 3 minus 1, which will be 0 to 777, right, in octal. In total 778, and this is a couple of example of octal number. Similar thing is true for hexadecimal. When counting in hex, each digit position can be incremented from 0 to f. Once a digit position reached the value f, it reaches to 0, and then next digit position is incremented. So this is an example of hexadecimal counting, right? So with n hex digit position we can count to 0 to 16 to the power n minus 1. So and in total is 6 to the power n, which is 0 to triple f. This is 3-bit. So for 3-bit hex it is 0 to triple f. Positional notation. This is also important. So the decimal number system. We know decimal number system is 0 1 2 3 4 5 6 7 8 9, something like that. But you need to know the position. So you have given an example 7594. So this 10 means the base 10 is decimal number, right? So whenever you're writing in terms of positional notation, so it will be 7 into 10 to the power something, then 5 into 10 to the power something, 9 into 10 to the power something, 4 into 10 to the power something. So it starts with here actually, the last least significant bit. 4 is least significant, 7 is most significant. So it will be 4 into 10 to the power 0. So the 0 position starts here, okay, from the least significant bit. Then this 9 into 10 to the power 1. So this is the first position. This is, or this is 0th position. You can say this is 1 position. This is 2. 5 into 10 to the power 2. 7 into 10 to the power 3. It goes on, right? So this is the general equation actually. So how general fund can be represented, and this is for decimal point. If you have decimal point 2 into 10 2.75, this is decimal number, right? So if you have dot here 2.75, so for decimal point what you can do, so it's saying it starts from 2 into 10 to the power 0, but for this one 0.75, so it starts from this side, right? 7, so 7 into 10 to the power minus 1, 5 into 10 to the power minus 2. If there is one more bit, then maybe 1, then it will be 1 to 10 to the power minus 3, something like that, right? So this is the general representation. Other number system. For binary basis 2, weights in power of 2. Binary digits are 0 and 1. For octal basis 8, weights in power of 8. Octal digits are 0 to 7. For hexadecimal basis 16, weights in power of 16. Hexadecimal are 0 to F. So you need to remember this number, because we'll be doing the conversion from one number system to another number system. So if you don't know the number, then you can do the rest of the part, you cannot follow. So if you do the summation, so it becomes 5 into 8 to the power 2, it becomes 320, 7 to the power 156 for this portion 2, and for this portion 0.75, altogether 378.75 decimal. So 572.6 octal is equivalent to 378.75 decimal, right? Similarly, here is the octal value 2a.8. So base is 16, so it will be a means 10 actually. So as we are converting to decimal, so you need to write 10 instead of a. So 10 into 16 to the power 0, 2 into 16 to the power 1, and for 8 into 16 to the power minus 1. So if you do the summation, it will be 14.5. So 2a.8 will be equivalent to 14.5. Similar thing here, 341.24. This is your pental. So the base is 5, so it will be 1. So 1 into 5 to the power 0, 4 into 5 to the power 1, 3 into 5 to the power 2, plus 2 into 5 to the power 1, plus 4 into 5 to the power minus 2. So altogether it will be 96.56. So this equivalent decimal is this one. Decimal to binary conversion. So there is two methods. Sum of weights method is the first method, and second is repeated division by 2 method for whole number. So repeated multiplication by 2 for fractions. So in method 1, decimal to binary conversion, say you have 45 decimal and you want to convert it in binary. What you can do, you can write this, you can make a fraction, something like that, split it down, something like that, 32,841, altogether it will be 45. But advantage of doing this is you can represent this in terms of 2 to the power something, like 32 for 2 to the power 5, 8 for 2 to the power 3, 4 for 2 to the power 2, 1 for 2 to the power 0. So if you consider about the position, this is 0 position, 1 position, 2, 3, 4, 5. Actually basically here, so 2 to the power 0 you have, 2 to the power 1 you don't have, that's why you put 0. So 2 to the power 2 you have, 2 to the power 3 you have, 2 to the power 4 you don't have, you put 0, 2 to the power 5 you have. So if you consider all of these values as 1, say 2 to the power 5 1, 2 to the power 3 1, 2 to the power 2 1, 2 to the power 0 1, because this could be represented in terms of 1, and for 0 it could be represented 0. So if you represent that way, so that will be equivalent decimal, equivalent binary for this decimal. Same thing is for this example. You have 76, so you split it 64 8 4, and you split it this way, to the power 6, to the power 3, to the power 2. For all other values 0, so consider this 0 0, this position 1, this 1, this 0, this 0, this 1. So this is equivalent binary for 76.